Okay, so in this module, we look at the problem of information cascade, which is like you have a set of initial adopters of some decision, say in a network. How soon that decision will spread to the entire network. Okay, so if you look at this problem, let us say, for example, in this case, you have V and W, say, have adopted to say vote for some candidate, and say that is green in color. Now, can this will can this influence everyone else in the network also to vote for the same candidate or not? Okay. Now, so that spread, okay, has to start with the neighbors of the initial adopters and then their neighbors and so on. Okay. So, like I show here, after given this initial adopters, first R and T will adopt the same, and then because of that, S and U end up adopting the same. So the critical question that we have to answer is what proportion of the neighbors should adopt a decision before a node starts adopting it. Okay. Now, why this problem is considered like this? Why the neighbors are considered to be more important to influence the decision? So, even if you take in our day-to-day things that we go through, for example, even though people might have come across or they would have come across a technology much earlier, they would not use it until the neighbors or whoever they deal with use that technology. Okay, so that means, so how many of your neighbors need to use that particular technology before you start using it? Okay, so you can think about it like that. So that's the kind of problem we're going to look at in this module. Okay, so the critical thing is what proportion of your neighbors should adopt a decision before you start adopting the same. So the process we are going to go through is this. So given some initial adopters, we'll say a user will adopt the same if at least q fraction of his or her neighbors are adopting the same. And the adoptions take place sequentially in what is called ticks or iterations as information about the adoption cascades through the network. And we stop the process when either all the users have adopted the same decision or no user have adopted a decision in a particular iteration or tick. Okay, so what is more important is what is this largest value of this fraction q that will enable all the users in the network to adopt a decision. And such fraction, the largest value of the fraction q, is called the cascading capacity of the network. So take this problem. So this is the given network, and V and W on the initial adopters, and let me say this q is 0.5 or 1/2. That means each node will adopt a decision if at least 1/2 of its neighbors have adopted the same decision. So given these initial adopters, what we find for each node is what fraction of the neighbors have adopted the decision. So for node R, it has 3 neighbors and 2 of its 3 neighbors have adopted the decision or to turn green. Okay, so the what is called the adoption value for R is 2 or 3. Now what about S? So for S, only one of its neighbor have adopted the decision. So it's going to be 1/3. 1/3 of the neighbors of S have adopted the decision. Now for T, it's again 2/3 of its neighbors are adopted. For U, again 1/3 of its neighbors have adopted. So now in the first iteration, we will make nodes whose fraction of neighbors who have adopted is greater than or equal to this Q. Okay. So in this case, R and T will adopt the decision to turn green. Now, because of that, the numbers change for S and U. So now for S, two-thirds of its neighbors have adopted, and for U also two-thirds of its neighbors have adopted. So in the next iteration, S and U will turn green because their fraction of neighbors who are adopted is greater than or equal to 0.5. Now, if you look at it, is Q can be only 1/2? No, Q can take a lot more values if possible. So, for example, Q could be 2/3. If Q is 2/3, again R and T will adopt to turn green in the first iteration. So, as long as the fraction of neighbors is greater than or equal to this Q, nodes will start adopting a decision. Okay, so Q could be two-thirds, right? Now, can Q be more than two-thirds, 2/3? So, say for example, Q is 0.8. Then, given this initial adopters, will R and T make an adoption in the first iteration? No, because the fraction of neighbors of R who have adopted the decision to turn green is two-thirds, which is 0.67, and it is not greater than or equal to 0.8. So R will not adopt it. Similarly, T will not adopt it. So that means if R and T are not adopting it, then S and U will not be adopting it because the network will remain the same till the end. Nobody else other than B and W will be adopting it. So that means the largest value of Q that will facilitate the entire network to adopt the decision is called the cascading capacity of the network. So in this example here, again remember, given the initial adopters, so we cannot right away come up with the cascading capacity of a network without knowing the initial adopters. Okay, so given these two initial adopters V and W, the cascading capacity of the network is two-thirds. Okay, so that's what I state here. The cascading capacity of a network depends on the network structure, which is like the distribution of the nodes and edges, as well as a small choice and the number of initial adopters. So it's not that if we have two initial adopters, we are going to have the cascading capacity of the network to be two-thirds. No, it depends on who are those two adopters. So it depends on all these things: the network structure, the choice of the initial adopters, as well as the number of the initial adopters. Okay. So now for a given set of initial adopters, like in this case two initial adopters, and who are those two initial adopters, the estimated cascading capacity of the network cannot be more than the maximum of the cascading capacities of the neighbor nodes of the initial adopters. And that's what we see here. The cascading capacity of given this V and W as initial adopters, the cascading capacity of the network cannot be more than the maximum of the what is called the cascading capacities of the neighbor nodes. So we say this two-thirds or whatever the numbers we have here as the cascading capacities of the nodes, because that's a fraction of the neighbors who are adopted. So it cannot be more than the cascading capacity of the network cannot be more than the maximum of the cascading capacities of the neighbors of the initial adopters. So it cannot be more than two-thirds in this example. Okay, so in real world, for a very large complex network, social network, the number of initial adopters is significantly smaller than the size of the network, but should be strategically chosen. So typical choices for initial adopters are the nodes with largest closest centrality or nodes that are part of a minimum connected dominating set and so on, and we'll see these things in details as we proceed. Okay, so let me stop here.